gum. So this chapter is going to be about functions. We're going to talk about power functions, polynomial functions, rational functions. We're going to talk about how to graph them, how to analyze them, how to solve them, okay? And we're also going to solve some word problems that involve these types of functions. So first of all, we have what we call a power function. This is any function that has this form, okay, where a and n are constants and you have x raised to a certain power, okay? So for example, 5x to the 4, 3x squared, these are all different types of power functions. In the case that the functions are monomials, we can talk about how they look. So if n is even and a is positive, all right? So where you have, let me just write that bigger here. So we're talking about n being even, meaning the x squares and x to the 4 and x to the 6, x to the 8. In the case that a is positive, so positive 2x squared, positive 4x cubed, x to the 4th, it looks like this, okay? Where both ends of the graph are up. It looks like a parabola that opens upward. The domain is negative to positive infinity. The range you can clearly see is from 0 to positive infinity. X and y intercept are 0. Now, of course, this is the basic parent function, right? And you can translate this, but this is what the basic function looks like. It's continuous for its entire domain. There are no discontinuities. It's decreasing and then increasing, okay? And the end behavior is such that at positive and negative infinity, both ends are going to positive infinity. Okay? Now, when a is negative, so for example, if you have negative 2x to the 4, okay? You still have something that looks like a parabola, but now because it's negative, because the a is negative, it's facing down. The domain remains unchanged. The range now goes from negative infinity to 0 because you have the negative portion of the y-axis. X and y intercept are the same. Continuity is the same. Symmetry is the same. The difference is that now it's decreasing from 0 to infinity and it's increasing from negative infinity to 0. So all this you can tell. And the big difference is that the end behavior is that both ends go to negative infinity, whereas before both ends went to positive infinity. Now, if you have an odd exponent, so for example, x cubed, and if you have positive 2x cubed, then it looks like this. This is an odd function now. One arm goes up, the other arm goes down, okay? And if it's positive, then the right side is up and the left side is down. Okay, and you can go through the rest of it. It's continuous everywhere. It's increasing everywhere. Okay, even if you think that here it's leveling off, it's not. It's slowly increasing. And the end behavior is such that at negative infinity, it goes down to negative infinity, and at positive infinity, it goes up. When n is odd, so if you have negative 2x cubed, then it's a reflection around the x-axis. So now, on the left side, it'll go up, and on the right side, it'll go down. Okay, and you can see the change here in the end behavior. Again, decreasing everywhere, but continuous everywhere. Okay, we're going to graph this function. We're going to describe the domain, range, intercepts, end behavior, continuity, and so on. So this is half x to the 6th. If it's x to the 6th, this is an even exponent. It means both are, it's an even function, so both ends are either up or down. In this case, it's going to be facing up because a is positive. Okay? So the y and x intercepts are both 0, 0. And we can just put some points in here. So when x is equal to 1, y is equal to a half, and it's symmetric this way. Okay, now what about when x is equal to 2? What would that look like? What's 2 to the 6th? 64 over 2, it'll be 32. Now that's a really high number, right? That means this is going to be a very, very narrow parabola. Still though, what is the domain? Negative infinity to positive infinity. The range is 0 to positive infinity, and it includes 0. X-intercept is 0, 0. Y-intercept is 0, 0. End behavior, as x approaches negative infinity, y approaches positive infinity, and it's the same here. Continuous on its entire life. Okay, now it's increasing from 0 to infinity, and it's decreasing from negative infinity to 0. All right? You see how we did that? Now, here I have negative x to the 5th. X to the 5th is an odd equation, odd power, so it's an odd function. That means one end will be up, one end will be down. Because it's negative, then the left end is going to be up. Okay? So, at 0, y is 0. Now, at negative 1, y is 1. At positive 1, y is negative 1. Okay? Now, what about at 2? 2 to the 5 is 32, right? So at x equals 2, it's negative 32. X equals negative 2, it's positive 32. So it's a very narrow graph. It increases very, very rapidly. Okay? Now, what's the domain? All real numbers, negative to positive infinity. We like these, right? And we already know that polynomial functions have a domain of all reals. The range, all real numbers. X-intercepts, Y-intercepts. End behavior, at negative infinity, f of x is, and here, negative infinity. Continuous, everywhere. Increasing, never. Never. And it decreases everywhere. Okay? I would like to graph that one on the calculator. So this is going to look like what? It's 2x to the negative 2, meaning it's 2 over x squared. 2 over x squared, right?
Oh, wait, no,
Okay, so let's graph this one. It's 2 times x to the power of negative 2. Oops. Zoom 6. Okay, that's what it looks like. Okay, now we know that 1 over x looks like, you have one arm here and another one here. In this case, it's 2 over x squared. Okay, so you cannot have any negative y values, right? Because everything is being squared. That's why everything is above the x-axis. Do you see what I mean? Okay, so it's important for us to think in those terms. So when we start to graph this, what I'd like us to do is in trace mode, okay, I just want us to pick some points. So when x equals 1, y is 2. So in trace mode, type in the number that you want. Okay? And now when x equals 2, type 2, enter, x equals 0.5. Okay? And it obviously is going to be totally symmetric here. All right? And the rest, you know you have an asymptote on the x-axis. You know you have an asymptote as the y-axis. So you're going to make it as accurate as you can. Okay? It's not supposed to cross the x-axis. I had a little trouble with the screen. I'm sorry, the y-axis. No, it shouldn't. So, okay. So the domain, all right, is all reals except for 0, meaning everything from negative infinity to 0 and 0 to positive infinity. The range goes from 0 to positive infinity, but we're not going to include 0 because that's an asymptote. The x-intercepts, none. The y-intercepts, there are none. End behavior. As x approaches negative infinity, y approaches 0. And as x approaches positive infinity, again it's 0. It's continuous on its domain, so from negative infinity to 0 and 0 to positive infinity, so there is an infinite discontinuity at 0. It's increasing from negative infinity to 0 and decreasing from 0 to infinity. Okay? So what we did in chapter 1 was lay the groundwork. Okay? Now you know. Now we're using it. We're combining everything in chapter 1 into one problem. Right? So, okay. Radical functions are expressions that have rational exponents. Okay? And we know that when you have rational exponents, you can also translate them into radical form. So, for example, x to the p over n becomes nth root of x to the p. And just a little bit of terminology, what is n called? It's the index. This is called the index. Okay? Here. Okay? So that's called the index here. So the denominator of the rational exponent is the index. Okay? It's that root. It's the nth root. So this is now a radical function. N and p are positive integers. Okay? And they are greater than 1. So, okay, so here's how things look. When you have an even root, okay? So, for example, if you have the square root of x, the fourth root of x, okay, when n is even, this is how the graph will look. All right, so basically, the domain is from 0 to positive infinity, and it's continuous. When n is odd, so the cube root of x, the fifth root of x, okay? This is now the inverse of the cubic function. You remember what the cubic function looked like? Was this. Well, if you take the inverse, then it's the cube root of x, which looks like this. So domain and range get switched, right? And the way it looks will get switched as well. So if you look at this, on what domain is it increasing? Where is this increasing? From where to where? From negative infinity to positive. It's increasing all the time. Okay? It's increasing all the time. All right? So, let's graph this one, and we can use our calculators to do this.
Are we going to have some cases or test this chapter where we can calculate?
Yes.
Is that permanent?
So, here, we're going to have 5 square root, square root 2x cubed. Yeah. It is a tall graph. So when we change the window to, let's say, 30. Oh, sorry. I changed the other one. Well, what I'm going to do is this. I'm going to go from -1 to 10. And what I'll do is zoom fit, zoom 0. That will adjust the y-axis so everything is visible. Okay. Square root means everything inside should be positive. Now, because you have x to the power of 3, right? That means if you were to put a negative x in there, it would leave it as a negative number, which can't happen in a square root. That's why, because the x is raised to a power of 3, we can only put in there positive values for x. Okay? So if this was x to the positive, x to an even number, like x to the 4, then we could have put positive or negative values for x in there. Okay? All right. So, again, trace, and I'm going to put in there x equals 1, y equals 0.7. Oh, 7.7. 7.07. So here. And when x equals 2, it is a very big number. Okay? So it goes up. Actually, you know what I would like to do is I would like to modify the calibration here. So I'm going to make this 4, 8. Here, I'm going to change this.
Do we also change the x-axis then?
No. You do not have to change the x-axis. So when x equals 1, we were at 7. And x equals 2, we're at 20, so it looks like this. Okay? All right. Back here. Feel free to modify that calibration anytime. Okay? Back here, the domain then is from 0 to infinity, and we can have 0 in there. The range is, again, same thing. X-intercepts, 0, 0. Same with y-intercepts. Yes. Left behavior. Okay, so when x approaches negative infinity, that's an invalid question. So just say none or NA. Okay? As x approaches positive infinity, we go to positive infinity. It's continuous from 0 to infinity. Now, when it starts off like this, at some point, at the end point, leave the bracket, leave the interval open. Okay? Because to the left of 0, it's not continuous. All right? Increasing from 0 to infinity, and it's never decreasing. Okay. I said none. So this one. So this is the next function we're graphing. I actually don't need the parentheses here. Zoom 6. Now this is a cube root with a translation, all right? So again, second calc, trace, all right, at 0, y equals 4. And if you're asked to label, you can go ahead and do that at this point. At x equals 1, y is 1.4. At x equals 2, what is y? 0.9. At x equals -1, it's 4.8. And at x equals negative 2, it's at 5.22. Now, an important number, an important point that you also want to include absolutely is the 0. So second calc, 0. Here's the left bound and the right bound. It's at 5.6 and 0. Okay, so all right. So we can quickly do the rest. Domain is all reals, as is the range. X-intercept was at 5.6. Y-intercept 0 and 4. End behavior, as x approaches negative infinity, we're going to positive infinity. No. So it's a cube root, which means it's continuously going to go up, and here it's going to go to negative infinity. It's continuous everywhere. It's not increasing anywhere, so none. And it's decreasing from negative to positive infinity. Mm-hmm. Now, solving radical equations. To solve radical expressions, first we would like to isolate the radical expression. It means make sure it's alone on one side. Raise each side of the equation to the power equal to the index. Okay? And solve for the indicated variable. The most important thing is to check for extraneous solutions. Extraneous solutions are solutions that will show up when you do the mathematics of it, but when you plug it back into the equation, they don't work. So they're extra solutions that show up, which you then have to eliminate. Okay, so in the case of this one, we would like to isolate the root, so we take the 3 to the other side. Now, square both sides. Because the index is a 2, we square both sides. Just be careful here, so we get 4x squared plus 12x plus 9 equals 28x plus 29. Always get 3 terms when you square a binomial. So now, magically, the root went away. And all you have is a quadratic equation, which we know how to solve. So bringing everything to the same side, 4x squared, 12 minus 28 is negative 16x. 9 minus 29 is negative 20, equals 0. I can divide everything by 4. And I can easily factor this. X minus 5 plus 1. X equals 5. X equals negative 1. But does it? So now we check. Okay? So first let's take x equals 5. Does 2 times 5 equal the square root of 28 times 5 plus 29 minus 3? So does the left equal the right side? What do we get on the right side? So 10 equals 10, that means yes, x equals 5 works. What about when x equals negative 1?
Probably doesn't.
Does negative 2 equal negative 28 plus 29 minus 3? This is 1 minus 3 is negative 2, so yes, so both of them work. Okay? All right, so now let's do this one. 2 more. Okay, so this is 4 equals cube root of x minus 2 squared. Now we raise everything to the power of 3. And 4 cubed is what these days? X minus 2 squared. And here we have another exciting feature here. What do we do now? Square root.
Oh my god. Oh, I didn't even think of that.
It's so perfect.
It's wonderful. So 8 equals plus or minus x minus 2. No. Plus or minus 8 is equal to x minus 2.
Oh god, this is not beautiful.
So now x is equal to 2 plus or minus 8, which means x is equal to 10 and negative 6. So let's check. X equals 10 means, does 12 equal the cube root of
No, it doesn't.
10 minus 2 is 8 squared plus 8?
Equals 12, not 10.
No?
Equals 12.
Does 12 equal that?
No, because wait. 64 to the third is 4 plus 8. Oh, they do equal. There's 3 root 8 squared, it's not just root squared.
And you substitute 8, not a 10.
No, it's 10 minus 2, which is it.
No, the answer, no, x equals 10. So yeah, then you do 10 minus 2, you get 8. And then it's just square.
So here too, we get 12 equals 12. That means both of these work. Okay. Now, this one, I need your attention for this one. When you have more than one radical in an equation, you want to isolate one of them. So you're allowed to have at most one radical on either side of the equation. Okay? So this, for example, is okay. If the two radicals were on the same side, you would bring one to the other side. Okay? So in this case, what we're going to do is we're going to square this as is, because it's already prepared for us. Now, here we get x plus 1 equals. When you're squaring this, you square 1, you get 1. You square the last term, you get plus 2x minus 12. And the middle term is 2 times, so positive 2 times the square root. Okay, that's a critical step. All right, so now this is x plus 1 equals 1 minus 12 is negative 11 plus 2x plus 2 times the square root. So you add 11 to this side and you get 12, and you subtract 2x, so you get negative x plus 12 equals 2 times the square root of 2x minus 12. At this step, if the left side was all divisible by 2, then I would have gone ahead and divided. But since x isn't divisible, just leave it the way it is. Now I still have a radical. It means I need to square one more time. So I square this, and I square this. When I do that, here I get x squared minus 24x for the middle term plus 144 equals, here's where students make a mistake almost all the time. They forget to square the 2. So it's 4 times 2x minus 12. Okay, this needs to be squared. Okay? So
Just go on to the regular.
now it's just a quadratic equation. Okay, so we have x squared minus 32x plus 94, 96. Oh, you go up. So it's
Minus 14.
so we're gonna square, and I'm sorry, we're gonna factor.
Yeah. We have to do
So we're gonna get 24 and 8. Negative 24.
Which one's minus?
It's almost like you went ahead.
Okay, so x equals 24. Okay. And x equals 8.
Let's go back.
All right, so when we check, when you put x equals 24 into the equation, we have the square root of 25 on one side. Does that equal 1 plus the square root of 50 minus 12? No.
No, it's 5 equals 7.
And here, when x equals 8, we have the square root of 9 on one side. 1 plus the square root of 2 times 8 is 16. Minus 12 is the square root of 4. Plus 1 is 3. So yes, you get 3 equals 3. So that works. That means x equals 24 is an extraneous solution. X equals 8 is the only solution. Now, in the case where you do have an extraneous solution, including that one, including x equals 24, is just as bad as leaving out one of the answers. Okay? So you have to recognize that it's wrong. So if you put in x equals 24, you get points taken off. Okay? All right.
What would come up with x equals 24?
Nothing. So at x, next week is Maroon Week. That means this is due on Monday.
There's a more.
What is usual?
Why did it show?
Okay.